Are you using resonators in your research, or perhaps developing resonators themselves? In both cases, the ability to measure the center frequency accurately and to understand how that center frequency changes with the environment is critical to driving this growing research field forward. I'm joined today by Jim Phillips from Zurich Instruments USA. Jim has had a long and successful career in research, including developing the world's most accurate distance measuring device at the Harvard-Smithsonian Center for Astrophysics. Jim will join us today to talk about the latest innovations in resonator characterization. It's great to have you here, Jim. Thanks for coming over from the US.
Great to be here, Tim. Thanks for having me. It's just wonderful to be back in Zurich.
Jim, tell us about the latest innovations in measuring resonators.
We actually have some exciting new results in measuring a resonator, and a new method for the resonators called Drever Hall, or PDH sensing. It was invented in the microwaves decades ago, and it's become an absolute standard in optics. In fact, I used it myself for several decades. And now we're able to bring it back to the microwaves. So the standard way of measuring a resonator in these frequency ranges is a phase-locked loop, or PLL. And we're finding that you can get up to 10 times more accuracy by using PDH. And the beauty of it is you can do it with your Zurich Instruments microwave lock-in amplifier, just using it in a different way.
This sounds like a big step forward in resonator characterization. Can you tell us a little bit more about how PDH has advantage over PLLs?
PLLs are simple and ubiquitous. There's one drawback, which is that there are numerous sources of phase error. And to a PLL, a phase error looks exactly like a frequency shift. So these sources come from wiring, cables that have capacitance and standing waves. All of these are phase errors. To PDH, these effects are invisible. So when you measure your resonator with PDH, you're going to get, on the average, you're going to tend to get a more stable result.
Could we circle back a little bit to ask about how did PDH come about?
In the 1940s, R.V. Pound, working at Harvard, developed PDH for the microwaves. Then Drever and Hall picked it up, and it's become enormously popular based on their work in the optical. It's absolutely standard for measuring an optical resonator. In fact, I used it myself for several decades in the optics. Now we're very happy to bring it back to the microwaves.
You mentioned that PDH is insensitive to phase noise. This sounds fascinating. Could you elaborate a little bit on this?
Sure. Phase lock loop probes the resonator with a single tone and measures the phase shift on that tone imparted by the resonator. The PDH, on the other hand, probes the resonator with a frequency modulated tone equivalent to 3 separate pure tones. When the frequency of the resonator is off from the frequency of the oscillator, then some of that FM is converted to AM, and we measure that AM. And the strength of the PDH method is that it effectively takes a double difference of the signals at those 3 tones. The phase errors tend to be common, so they cancel very nicely in that double difference.
Great, thank you. Jim, the ability to essentially cancel out these parasitic effects is very important, and I can really see the benefit. Have you tried this in the lab?
Yes, we have. We're working with Johannes Paulanen and Pranaya Rath at Michigan State University. We've taken a 1 gigahertz surface acoustic wave, or SAW, resonator and locked a PLL to it. Simultaneously, we monitored the frequency with PDH. Then we disturbed the resonator by dropping a small weight on the cables. And the PLL would see spikes in the frequency and a drift slowly afterwards. The PDH saw much less of this. In fact, the PDH record looked essentially flat.
Nice.
In another experiment, we set up a resonator to run overnight, and we monitored it with PLL and PDH. Then we computed a measure of the frequency stability, which is commonly used in the resonator business, called the Allen deviation. The Allen deviation for PDH was as much as 10 times better as that for PLL.
Very impressive, thank you. It's important to understand that these cables can be a source of error, and it's absolutely fantastic that you now have a method for excluding these. How can this be used by researchers to optimize their measurements?
Tim, I think that if people are measuring their resonator with a PLL, they risk leaving great performance improvements on the table. With PDH, you can pick those up. So in the Zurich Instruments US lab, we set up a resonator with 30 centimeter cables. The normal setup in a Dewar or in any other normal setup frequently requires a cable. So the improvement you get depends on what the cables are and how much they're varying. We find that if you just leave a resonator and try to have it just sit on the table, there are little variations that PLL thinks are frequency changes and is actually ignorable by PDH.
Can you tell us how PDH works so well on Zurich Instruments products?
Certainly. Traditionally, these measurements, PDH in the microwave and lower frequency ranges, have been taken with an analog frequency modulator. That component has a limited dynamic range. On the detection side, the AM has been detected with an analog power detector, again having a limited dynamic range. So with the Zurich Instruments digital lock-in amplifiers having the mod option, the generation is fully digital and improves the dynamic range. Likewise, on the receive side, the detection can be 3 separate digital demodulators, again improving dynamic range. By the way, we think that this is the first time that PDH has ever been used with direct detection of the 3 separate tones. And Zurich Instruments lock-in amplifiers make it easy.
That's great to hear. Are there any other places where PDH could be useful?
Yes, there are. PDH also works in the radio and audio frequency ranges. We've focused on the microwaves, but we're excited to try out the radio and audio ranges, so I particularly encourage people to get in touch with us about work in these ranges, because PDH is quite new there, and I think there are some improvements waiting to happen.
So how do people get started on this?
Just contact us. Tell us about your measurements and what you need. We will tell you how PDH works. We'll set you up with the required instrumentation, and you will cable your resonator just the way you do for a PLL, and you can be doing PDH right away.
Thanks, Jim. Really appreciate this fantastic overview.
Great to be here, Tim. It's a fun subject.
Well, there we have it. If you're measuring with resonators or developing them, we've seen today that PDH can improve your measurement precision by up to 10 times. And they can also help to reject parasitics coming from your cables or wiring. If you'd like to learn more or set up a demo, please get in touch. Thanks for watching.